I'm back. Hopefully that wasn't too long of a pause. Now we're going to take a look at a cylinder problem. It's still very similar to the previous one. Let's see, a city's water tower is a simple right cylinder. So as I draw a picture of a cylinder, again, for related rates, a good picture is worth a lot. So there we go. The cylinder is 50 feet tall and has a diameter of 15 feet, it looks like. Usually, if the diameter is 15, oftentimes we want to also use the radius for things. So the radius would be 7.5. The height of the water of the cylinder is dropping 3 feet every day. How fast is the volume changing? So I've got a picture. That's kind of step one for most related rates problem. The next thing you want to start doing is laying out all your variables. What variables do we have, and are they changing? I've actually already got R here. So if I look at other variables, we've got the height of the cylinder. And then we've got volume also. So we've got three variables here, R, H, and V. Then I want to think to myself, are these variables ever changing? So think about the water in this cylinder. It is, of course, dropping 3 feet every day. However, even when it's from the top to the bottom, it's still filling the entire circle, so the radius is never going to change. Alright, the radius is not changing. Okay? However, the height definitely is. So in this problem, if the height is changing, that means it has a derivative. And so we're going to want to think about that derivative. And of course, as the volume is changing, that means the volume changes. So we have a dV dt also. Now we can start thinking about some equations. What equation can we use here that relates all three of these variables? The volume equation. The volume of a cylinder is pi r squared times height. As you can see, we got all three of our variables here. And then we want to think, alright, which of these variables don't change? R does not change, so we can actually plug in R right now. Pi times 7.5 squared times H. Because R is not going to change, I can plug that in right now. And so volume is equal to 7.5 squared 7.5 times 7.5 56.25. And we still have times H. So V and H are both changing, so they have to stay variables. Alright, but if we want the derivatives, we have to take the derivative of both sides. The derivative of both sides. dV dt is what we want, so that is going to stay. On the other side, we've got the derivative of 56.25 pi times h. There's only one variable, so that doesn't look too complicated. Remember that this in front here is just a number. So it's like 5 times h. And the derivative of that times h is just the number. So 56.25 pi. But of course the variables don't match, so we have to add a dh dt, and that is dv dt. And thankfully we're told what dh dt is. If we go back into our problem, dh dt is how the height is changing, and they tell us the height is dropping 3 feet every day. So I probably should have gone to the beginning of my problem and realized that dh dt was negative 3 feet per day. Forgot to do that. But now we can plug that in. So we have 0.25 pi times negative 3, which multiply those together times 3, 168.75 pi, which if you want to multiply by pi on your calculator, go ahead. Be that times 3 approximately. 480 something, I want to guess. 490 maybe. Oh, negative. Alright. And that is feet. Oops, not necessarily feet. Where are you? So what are our units? We're dropping 3 feet. So we are going to use feet, but we're talking about volume, the change in volume with respect to time. Volume is cubic, so we're cubic feet. And our time measurement was day, so that's going to be every day. So approximately negative 480 maybe cubic feet a day. Alright, that's the second one. Hope that's starting to make some sense. I'm going to make a new video for the next one. I think we've got 2 more, guys. Just 2 more.